This vast universe of ours and its phenomena are governed by certain physical laws, which can be difficult for anyone other than a scientist to understand. The search for these laws began in the age of Galileo and Newton. But it was in the 19th century that science was able to formulate several of these laws in a way that accurately described many natural phenomena of the physical world. How to get off a moving vehicle safely. How much strength the concrete used in a building should have. How much current flows from a given voltage. How aerodynamic principles should be used while designing an aeroplane. We have an accurate and proven reply to each of these questions. Words such as approximate and estimated have no place in the laws of the physical world, the world that is visible to us and whose phenomena can be measured accurately. We would probably have been quite happy in this world of ours if scientific exploration in the 19th century had not introduced us to that extremely small aspect of the physical universe known as the world of atoms. This was the world of those infinitesimally small particles that we couldn't see with the naked eye. But whenever we tried to understand this world and apply the laws of physics to it, we failed. These tiny particles had motion, but our laws of motion didn't apply. They had momentum, but the force generated by it had characteristics that didn't fit into the Newtonian framework. Newton had taught us that all natural phenomena could be described in precise mathematical form. But all his principles failed in the atomic world. Scientists call the big challenge posed by this tiny world quantum physics. The story of quantum physics' birth and development begins with the phenomenon known as black body radiation.
तो ये ब्लैक बॉडी रेडिएशन क्या है? बहुत सारे लोग पूछा करते हैं कि रेडिएशन में ब्लैक बॉडी रेडिएशन की चर्चा वैज्ञानिक करते हैं, तो इसमें क्या खासियत है? तो आप ऐसी कल्पना कीजिए कि एक बंद जगह में रेडिएशन है जो बाहर नहीं निकल पाता, वो उस बंद जगह में ट्रैप्ड है। तो ये रेडिएशन उस बंद जगह की दीवारों से टकरा के फिर इधर उधर स्कैटर हो जाता है। वो पहले जहाँ से निकला था वे जगहें गर्म होती हैं और जहाँ वो चलता है, जहाँ जिस तरफ जाता है वो जगहें ठंडी रहती हैं। तो जब ये रेडिएशन इधर उधर भटकता है तो एक ऐसी संतुलित अवस्था आ जाती है कि उस बंद जगह में सभी स्थानों पर वही टेम्परेचर, वही तापमान रहता है। तो ऐसी संतुलित अवस्था को हम लोग ब्लैक बॉडी रेडिएशन कहते हैं।
Broadly speaking, this can be compared to the thermal radiation inside a closed oven. When the pattern of this radiant energy was studied as the body's temperature increased, it was found that energy patterns were varying as per the frequency of the radiation. But while this relationship was known of, classical physics had no mathematical formulae to define it. Several scientists, including Kirchhoff and Wien, tried to understand this, but they weren't entirely successful. Ultimately, it was Max Planck who suggested that this thermal radiation was not continuous, emerging instead in discrete packets that he called quanta. He said that each packet had its own frequency, and the energy it contained could be expressed as a specific constant multiple of that frequency. So the variable pattern of black body radiation could be understood in this way. The constant has since been known as Planck's constant. H, this constant of Planck's, whose value was 6.63 into 10 to the power of minus 34 joule seconds, certainly solved the problem. But as to why this packet-based formula for energy worked, Planck had no answer. Towards the end of the 19th century, around 1898, J.J. Thomson had discovered the electron, and in the early years of the 20th, speculation about the structure of subatomic particles grew rapidly. A succession of new theories attempted to explain how electrons revolved around the nucleus of an atom. Scientists were drawn towards a planetary model, but this was wrong as per classical physics. The real culprit was Maxwell's electromagnetic theory. It said that the energy from a moving charged particle that was accelerating emerged in the form of electromagnetic waves. This meant that the electron, which was a negatively charged particle, would keep emitting electromagnetic waves and losing energy until it spiraled into the nucleus. All of this would happen in a very short time. So accepting this idea as true meant believing that atoms were inherently unstable, which was not the case. The Danish scientist Niels Bohr solved that puzzle. Bohr was studying the lines that formed the radiation spectrum of heated hydrogen. He said that the electron didn't emit any energy while orbiting. It was when it jumped from a higher energy orbit to a lower one that it released energy. This energy was released in the form of photons, massless particles of light. It was in packets, and it could be measured using Planck's methods. He said that if the frequencies of the lines in the hydrogen spectrum were multiplied by Planck's constant, one would get the amount of energy released by electrons when they jumped from higher to lower energy orbits.
तो प्लैंक का ये नियम और उसका ये गणितीय स्थिरांक उसने एक ब्लैक बॉडी रेडिएशन के पहेली को एक्सप्लेन तो कर ही दिया, लेकिन उसके साथ साथ ही नील्स बोर के एटॉमिक मॉडल को भी उसने अच्छी तरह से समझा दिया. तो ये गणितीय चमत्कार तो था ही, लेकिन इसके साथ साथ हम ये भी कह सकते हैं कि उसने कैसे इस सवाल का जवाब दिया, हाउ इसका जवाब दिया, लेकिन क्यों, वाई, इसका अभी तक जवाब किसी के पास नहीं था.
The question was, why did electrons, despite being particles, fail to behave according to electromagnetic theory? Because every charged particle in motion ought to have been governed by its laws, since they were well-established truths. Did this mean that electrons in orbit didn't behave like particles? This strange question had an even stranger answer. This was that electrons in orbit behaved not like particles, or in other words matter, but like waves instead. The scientist who arrived at this strange conclusion was de Broglie. Before this, Einstein had put forward a revolutionary idea, that light waves behave like collections of particles. This was demonstrated practically when light waves were directed at a metal plate and electrons were emitted, which could be measured in terms of electrical current. He explained this by saying that when light, in the form of particles, collided with the metal plate, it gave its energy to electrons, which then used this energy to emerge from the metal. This principle of Einstein's became famous as the photoelectric effect, and it won him the Nobel Prize. We see many examples of this effect in our daily lives, especially in gadgets that use photosensors. Once Einstein had made his formulation, there was no longer any doubt that light waves in the form of photons behaved like matter. In the meanwhile, de Broglie had put his ideas into mathematical form. He said that when an electron behaved like a wave, its wavelength would be equal to Planck's constant divided by its momentum. De Broglie proved this by studying the crystal diffraction pattern of electrons with energies of the order of 100 electron volts, where it could be seen that electrons, like waves, have diffraction patterns.
विद्यार्थी कभी कभी रोचक पर कठिन सवाल पूछते हैं। मुझसे एक विद्यार्थी ने पूछा कि जैसे इलेक्ट्रॉन के दो रूप होते हैं, वेव और पार्टिकल, वैसे क्रिकेट बॉल के क्यों नहीं होते। तो इस सवाल का जवाब इस तरह से दिया जा सकता है। अगर हम de Broglie का नियम लगाएं, जो हमें बताता है कि किसी भी कण के, किसी भी पार्टिकल के वेवलेंथ को कैसे नापा जा सकता, तो de Broglie का ये नियम है कि उस पार्टिकल के वस्तुमान को उसकी वेलोसिटी से अगर हम गुणा करें तो उसका संवेग मिलता है, मोमेंटम मिलता है। तो उस मोमेंटम से जब हम प्लैंक के कांस्टेंट को डिवाइड करते हैं तो हमें जो जवाब मिलता है वो होती है उस पार्टिकल की वेवलेंथ। तो जब हम इलेक्ट्रॉन या प्रोटॉन के बारे में यह नियम लगाते हैं तो हमें बहुत महत्व की वेवलेंथ वगैरह मिलती हैं। लेकिन अगर हम क्रिकेट बॉल पर यह नियम लगाएं तो क्रिकेट बॉल का वस्तुमान इतना बड़ा होता है और प्लैंक का स्थिरांक इतना सूक्ष्म है कि हमें जो वेवलेंथ मिलती है उस क्रिकेट बॉल की वो बहुत ही छोटी होती है, इतनी छोटी कि उसका कोई भी परिणाम हम नहीं देख पाते। तो ये एक बात अच्छी ही है कि क्रिकेट बॉल केवल कण के रूप में ही, पार्टिकल के रूप में ही हम देखते हैं, वेव के रूप में नहीं। अगर उसके भी दो रूप होते तो क्रिकेट खेलना बहुत ही मुश्किल हो जाता।
Bohr's atomic model provided a good basis for de Broglie's principles, because it said that the various orbitals in an atom were associated with specific energy levels, and that when electrons jumped from higher to lower energy levels, they emitted packets of energy that could be seen as photons, or in other words, light. At the same time, it was found that another assertion was true as well, namely that if the right amount of energy were given in the form of photons to the electron, then it could jump in the opposite manner, from lower to higher energy orbits. The revelation that electrons existed in different energy states in an atom also gave rise to a powerful new invention, the laser. Today, we're all familiar with this product of quantum physics, whether in engineering or the medical sciences. In quantum physics, we had given waves the freedom to behave like particles, and vice versa. But as to when exactly these transformations happened, there was no clear answer then, and there still isn't one. All that the scientist duo of Stern and Gerlach could establish through their experiments was that one could not predict just when an electron was going to behave like a wave or like a particle, because this was based on probability. Using de Broglie's formula for calculating the wavelength of matter waves or particle waves, it was possible to say the greater a particle's momentum, the lower its wavelength, which meant that its position could be determined with a fair degree of accuracy, since it was behaving more or less like a particle. Conversely, if the momentum were small, then the wavelength would be large, and the particle would occupy a greater space, like a wave, and behave like one. In 1925, Werner Heisenberg called this the uncertainty principle and worked out a precise mathematical formula delta P into delta X is equal to H for calculating the uncertainty associated with determining positions and momenta of elementary particles.
अनसर्टेनिटी प्रिंसिपल को अधिक बेहतर ढंग से समझने के लिए हम एक थॉट एक्सपेरिमेंट की काल्पनिक प्रयोग पर विचार करेंगे। ऐसा समझिए कि एक जगह एक इलेक्ट्रॉन है और हम यह नापना चाहते हैं कि वो कहाँ पर है और किस रफ्तार से जा रहा है। तो ये जानने के लिए हमें कुछ डिटेक्टर लाना पड़ेगा, अपनाने पड़ेंगे कि उस डिटेक्टर से उस इलेक्ट्रॉन की इंटरैक्शन हो जिसकी बदौलत हम यह जान पाएँ। तो सबसे सरल डिटेक्टर होगा प्रकाश की किरण, और प्रकाश की किरण अगर उस पर पड़ती है तो उसके धक्के से वो इलेक्ट्रॉन अपनी जगह बदल देता है और उसकी रफ्तार में भी परिवर्तन आता है, क्योंकि इलेक्ट्रॉन स्वयं बहुत हल्का होता है। तो इसका मतलब यह हुआ कि नापने की प्रक्रिया में हम यह नहीं जान पाते कि वो इलेक्ट्रॉन पहले किस दशा में था, किस स्थिति में था, और इसलिए हमारी उस इलेक्ट्रॉन को जानने के प्रयत्नों पर मर्यादाएं आ जाती। तो न्यूटन के ज़माने से ये एक विचार चलता आया था वैज्ञानिकों में कि हम किसी भी वस्तु को निश्चित रूप से जान सकते हैं कि वो आगे चलकर कहाँ जाएगी, किस तरह से उसमें परिवर्तन आएंगे, लेकिन यह जो निश्चितता है वो इन मर्यादाओं के कारण, अनसर्टेनिटी प्रिंसिपल के कारण अब संभावना में बदल जाती है। यानी हम प्रोबेबिलिटी के रूप में कह सकते हैं कि यह संभव है कि यह इस दिशा में जाए या इस दिशा में जाए, लेकिन निश्चित रूप से हम नहीं कर पाएंगे।
As it developed through the idea of wave-particle duality and the uncertainty principle, quantum physics reached a point at which it became necessary to understand the wave nature of particles and their behavior more thoroughly. What was needed was a mathematical model that could define all this in every way and for all conditions. Within a year of Heisenberg's postulating his uncertainty principle, Erwin Schrödinger came up with this mathematical solution, which described all the wave characteristics of particles satisfactorily. Even today, 80 years down the line, Schrödinger's wave equation is solving many scientific puzzles. Over the decades, quantum physics has continued its journey of exploration, but it has also taken new turns. Scientists working on Bohr's hydrogen atom model found it necessary to develop some new formulations when studies of the spectral lines of some complex atoms showed electrons in the same orbital behaving differently. Electrons that were identical in every other respect. This meant that electrons had some other quality that had so far gone undetected. This quality, when discovered, was called spin, because it referred to the electron's spinning on its own axis. It was found that the difference in behavior could be explained by the fact that the electrons were spinning in opposite directions. In 1925, with the help of these concepts, Wolfgang Pauli formulated his exclusion principle, which stated that no two electrons in an atom could be in the same quantum state. In other words, there would always be some difference or other in their energy, momentum, or spin. This spin idea, in fact, gave quantum physics itself something of a spin. The question of whether spin values for particles had to be integers or could be fractional values as well, led to the creation of a new field known as quantum statistics. Through this, the various kinds of behavior of particles was sought to be further illumined. But the formulae of quantum physics were found to be applicable in some ways to the behavior of large objects or objects with a large mass as well. And this was proved by the Indian-born Nobel laureate Subramaniam Chandrasekhar. He explained that when a star like the Sun expends all its nuclear energy, it begins to experience a gravitational collapse that packs its electrons closer and closer together. In this situation, Pauli's exclusion principle comes into operation. Because the principle sets limits on the packing together of the electrons, the contraction stops, and the star assumes a stable form known as a white dwarf. But for the Pauli principle to come into effect, the star's mass had to be within a certain limit. This came to be known as the Chandrasekhar limit, because it was Chandrasekhar who determined its value. But despite all this success, Einstein didn't consider quantum physics to be a complete science, besides finding it impossible to believe that the world was governed by Bohr's probability theory. As he put it, God doesn't play dice with the universe, or in other words, physical processes are not determined by the laws of chance. Somewhere, he believed, there was a definite pattern that we had failed to discover, and that was why the discipline seemed so indeterminate. Was Einstein right? Is there some law, some formula from which all the others could be derived? A law from the visible physical world or the atomic one? Even those who disagree with Einstein believe that the foundations of quantum physics are not yet as firm as they should be. With the help of probabilistic tools, we have been able so far to find fairly good answers to the question, how? Over the last 2 decades, work based on the calculations of the scientist John Bell has given clear indications of the accuracy of Bohr's probabilistic model of the atomic world. But we're still looking for the answer to why.